Alright, so this is a screencast to help prepare you for the midterm. We're going to focus on conservation of energy. Conservation of energy says that energy is never created, never destroyed, just goes from one form to another. So we're going to go back to the skate park and take a look at this guy. He's going to be starting with all potential energy. Alright, we'll start him at this position. I'll hit play. All that potential energy becomes kinetic, goes back to potential, becomes kinetic again. Let's review this. Go backwards and look at it step by step here. So it's all potential. It starts off with no kinetic. But as potential shrinks, the kinetic energy goes down. But the total energy doesn't change. He goes back up this hill. At the peak of this hill, he's gotten a lot of his potential back, but he still has some kinetic. He's still in motion. These two energies are still going to be adding up to the total. So as he's going along this roller coaster, his energy is going from kinetic back to potential. But for the vast majority of the trip, it is a combination of kinetic and potential. It's really only at this spot here that it's all potential. But whatever the case, that kinetic plus potential will always equal whatever that starting potential was. So let's take a look at the sample. Here's the problem from the test. We're going to look at calculate the velocities at points 2, 3, and 4. So remember, energy is never created, never destroyed. I'm just going to look at the 2 points, points 1 and 2. At point 1 is all potential energy. It starts off as all potential energy. At point 2, all that potential energy becomes purely kinetic energy, because this is effectively, this right here is our zero height. There's no potential energy here, so it's all kinetic. And I'm just going to label these. That's 1, that's 2. So this formula here is saying that the total energy at 1 is equal to the total energy at 2. Potential energy is mgh. Kinetic energy is 1/2 mv squared. This is the height at 1. This is the velocity at 2. Masses cancel out. We're going to solve for v. So v at 2 is equal to 2gh, but that's squared, so that becomes the velocity at 2 is equal to the square root 2gh1. Plug that into my calculator. Square root 2 times 9.81 times the height at 1 is 35. So the velocity at 2 is equal to 26.2, or we'll just leave it at 26 meters per second. Now, the velocity at position 3 is a little trickier because it's a combination of both potential and kinetic. So we're going to compare 1 and 3. Position 1, it's all potential. Position 3, it's a combination of potential and kinetic. So these two energies are going to equal the starting energy. This is mgh1, which is equal to mgh3 plus 1/2 mv squared, and that's the velocity at position 3. Now I can, what do I notice? If I divide this side by m, I can divide this by m, this by m. The m's all cancel out. Then I'm going to subtract gh3 from both sides. So I have gh1 minus gh3 is equal to 1/2 v3 squared. I'm going to solve this for v3. So if I multiply both sides by 2, I'll get rid of that 1/2, and then I'm going to take the square root of both sides. So v3 is equal to the square root of 2g h1 minus h3. I plug that into the calculator. Square root 2 times 9.81 times parentheses h1, which is 35, minus h3, which is 28. And parentheses, and I get 11.7. So V3 applying sig figs is 12 meters per second. Position 4 is done exactly the same way, only instead of using height 3, I'm going to use height 4. 1, 4. PE at 1 is equal to the potential energy at 4 plus kinetic energy at 4. Why? Because energy is never created or destroyed. So the total energy at 1 has to equal the two energies at 4. If I go through and do this algebraically, I will end up with 2g h1 minus h4. Because it's really the same process. So v4 is equal to square root 2 times 9.81 times h1, which is 35, minus h4, which is 15. 19.8, applying sig figs, that becomes 20 meters per second. Alright, so on either side of these equations, it's the total energy at one point is equal to the total energy at some other point. Number 2 is done exactly the same way. We're dropping a ball, so I'll just call that position 1, and right before it hits the ground is position 2. At position 1, it's all potential energy. At position 2, right before it hits the ground, it's going to be mostly kinetic energy, but it's also going to have lost energy from air resistance. And that energy probably would have been turned into heat, or the kinetic energy of the air molecules. From here, I can put in my numbers. mgh at 1, 1/2, mv squared at position 2 plus the energy of the air. mgh at 1 is mass 145 grams, which is 0.045 kilograms, multiplied by 9.81 times the height, which is 15 meters. I have to convert that grams into kilograms so that I get 21 joules. So that's 21.3 joules is equal to 0.5 times 0.45, 0.145 times the velocity squared, which was given here, 7 squared, 3.55 joules, plus energy of the air. So I have these two numbers. I'm going to solve this for the energy of the air, which is equal to 21.3 minus 3.55, giving me 1.3 minus 3.55 gives me 17.75 joules of energy. So this is the energy that was lost due to air resistance. This should be rounded off to 18 joules. And that's the answer. Many of you did this correctly, only you neglected to convert the grams into kilograms. And that is it for the energy. There will be a sample problem, or there is a sample problem posted for you to try out. If you successfully go through those sample problems and turn it in on Tuesday, I'll give you some extra credit. That's it. Good luck, study hard, and we will see you after the weekend.